Okay, so welcome all to this pre-recorded webinar from our own Dr. Ramez Elgammal, CTO of the Coretec Group. As I'm sure you are all aware, this year's battery show in Novi was canceled as a precautionary measure to deal with COVID-19 issues. We had intended to present at this show and are disappointed that we will not be able to do so. However, we wanted to be sure to give our audience the information about our material, cyclohexasilane, and its potential, particularly in the development of batteries for electric vehicles. So with that, I am going to hand over to Ramez, and I will follow up with questions that have been submitted through our website that Ramez will also cover. So I will hand it over to you, Ramez.
Thank you for the introduction, Michelle. And like Michelle said, I'm sorry that we couldn't deliver this in person, but we hope that being able to share this information with you, that you'll find it useful, and we're happy to answer follow-up questions whenever you like. So the title of today's talk is Tunable Syntheses of Advanced Silicon Anodes Using Cyclohexasilane. And I'd like to start out by just giving a brief overview of cyclohexasilane or CHS and some scope of the applications that we think CHS can find market penetration in, as well as some other related silicon-based materials that can be derived from CHS. So just a little bit of backstory on the Coretec group and technologies that we're developing. So we've recently developed several pieces of new IP, one related to a new synthetic route to manufacturing cyclohexasilane that we think should be highly scalable and will deliver commercial product in a variety of different markets. So that's one piece of IP we've developed. Second piece of IP that we've developed is related to using CHS to make new types of LED lighting, so specifically for generation of ultraviolet light, which has traditionally been a challenge. And in light of everything that's going on with COVID-19, the ability to have a UV light source as a disinfectant is becoming more and more important. So thinking about CHS as a molecule, though, so in addition to direct conversion of CHS to silicon-based devices, other examples to broaden the scope of its use include what I'm calling here is dope CHS, which is chemically modified CHS, deriving silicon-based nanoparticles from CHS in a high-yielding synthetic route is something that we're actively exploring. And so this idea of stacked polysilanes that can be derived from CHS. So these are macromolecular structures that have applications not just in batteries, but in all the markets that we're targeting here, as you see on the right, photovoltaics, flexible and printable electronics, and a more long-reaching one that we think can have a lot of impact is in drug delivery. So given that, as opposed to most commercially available nanoparticles, silicon is inherently non-toxic, and we think making CHS derived drug delivery vesicles is something that is worth exploring, and a wide range of deposition or manufacturing routes using CHS can be explored, and the two that we think are easiest to demonstrate are microcold spray and AP-CVD or plasma enhanced chemical vapor deposition. So as I said, there are a lot of markets that CHS can find use in. today we'll be focusing on batteries, but certainly there are a wide range of markets. So we filed some IP already on photovoltaics or where we'll find solid state lighting, LED, and related applications. So really, it just depends on the pathways to commercialization and customer discovery to find more uses for CHS. So just a little bit about the chemical properties of CHS. So it's a liquid at room temperature, so its melting point is 18 degrees Celsius or slightly below room temperature. And its boiling point is 226 degrees Celsius. And so at low pressure, so at 10 torr, it boils at 80 degrees. So it's relatively low boiling, and 10 torr of pressure is modest. And the shelf stability of CHS is, when stored in a proper container, is well over 6 months. And we were excited about our recent supply agreement with Evonik to be our global distribution partner for CHS. So comparing CHS to a wide variety of commercially available silanes. So one thing that, I guess two things that really highlight the why it has such unique properties are the comparatively lower silicon-silicon bond energies and the silicon-hydrogen bond energies. So this idea of having a lower bond dissociation energy ultimately leads to faster deposition rates and deposition at lower temperatures. So comparing it to, I guess, the most traditional silicon precursor, monosilane, so it requires a lot more energy to break those silicon hydrogen bonds in monosilane. And that's one reason why CHS is superior, is that the bond energies are lower, and it gives much faster deposition rates. And that deposition rate comparison is highlighted here in this slide, and this is using a technique known as aerosol-assisted chemical vapor deposition. And so here, we're looking at the deposition rate as a function, or the growth rate as a function of temperature. And so we see, I guess, first and foremost, with monosilane, you typically need temperatures of at least 600 degrees Celsius. So that requires highly specialized equipment, capital-intensive equipment. So looking at CHS instead, so we see deposition as low as 270 degrees Celsius, somewhere in that range. And so what this leads to is the ability, because you can deposit it at low temperatures, to have something that could be done first at atmospheric pressure, which removes a lot of the expensive vacuum equipment and offers the promise of something that's continuous and scalable. And so the industry term there is roll to roll. So having a silicon roll-to-roll manufacturing, especially for the manufacturing of silicon-based anodes, is highly desirable. And so in the table below, I just want to highlight some of the differences in the growth rate. So we see here that in a non-optimized growth rate of 17 nanometers per second, so comparing that to, I guess, traditional chemical vapor deposition, so we're anywhere from 1 to 3 orders of magnitude faster growth rate. And even with a newer technology like PE-CVD, we're anywhere from a factor of 3, maybe as high as 10 with a fully optimized process faster. So this roll-to-roll processing is attractive for a variety of reasons. So in a continuous process, you can have fabrication of your entire device. And due to the unique reactivity of CHS, you can co-add dopants. So if you want to make a doped silicon or a silicon carbon composite, you can feed both reactants in simultaneously, do the deposition in real time in a single step, and yield the desired product or in a high yielding way. So because this is happening, or the deposition is happening at a low temperature, so we see on the right an X-ray diffraction pattern for the sample. So in blue, that's the amorphous silicon that comes out of the process, and then in red, annealing at 400 degrees Celsius. So we start to see this transition from amorphous to crystalline silicon. So if the desired product is amorphous, that's difficult to do conventionally. CHS offers an easy way to do that. And so this idea of having fine control over the surface chemistry. So on the left, you see FTIR spectra that shows, so when CHS is converted into a silicon thin film, some of the silicon atoms are terminated with hydrogen atoms. And so through a hydrosylation reaction with 1-dodecene, you can passivate the surface and then directly have a surface functional group. So there are a wide variety of chemistries, way too many to mention here, but the idea here is that CHS allows you to have a thin film surface or a nanoparticle or quantum dot surface that whose surface chemistry can be easily modified for the desired effect. So another thing that's unique about CHS, so it's a liquid at room temperature, unlike monosilane or many of the commercially available silanes. So it can be processed in solution. And so you see here some micrographs of polysilane colloids, as well as amorphous silicon colloids that were generated from reaction in solution, either thermally or by ultraviolet irradiation. So we have very good size dispersion and a fine control over the particle morphology as well. So thinking now about making silicon thin films using PE-CVD, which is becoming the preferred method to make silicon-rich anode materials. Some advantages of CHS. So comparing it to monosilane, it has so in a single molecule 6 times as many silicon atoms. And so this is one reason behind the faster deposition rate. Other reasons I've alluded to before, the weaker silicon-silicon and silicon-hydrogen bonds. So in the past, we've demonstrated that high quality amorphous silicon with hydrogen termination films can be fabricated, and this can be done in a single step. So eliminating a lot of the costs associated with making such materials. And because CHS has a low vapor pressure at room temperature, it's safer to handle than gaseous silanes. And going back to the apparatus that I showed, so where CHS can be directly fed into the reactor without the need of dilution or carrier gas, and this greatly simplifies the operational process. So now looking at batteries, so thinking about where CHS might fit into the overall value chain. So we're looking at replacing the existing manufacturing process of the anode. So this figure is from that reference below from Presidia Manufacturing from earlier this year. So where instead of using monosilane, CHS would be the source of the active anode material. In this example, it's making silicon nanowires, which has been demonstrated in the past. And just thinking about comparing CHS to graphite, which is the conventional lithium-ion anode material, I want to highlight so the lower mass. So using silicon nanowires, we can reduce the weight of the battery, reduce the volume as well due to its higher capacity, while increasing the gravimetric and volumetric energy density. And so these costs here, and these costs were using monosilane. In this example, the comparable silicon anode can be manufactured on par with graphite, and maybe even a little bit less than the price of graphite. And that's very encouraging given its higher gravimetric and volumetric energy densities. So taking a look at some examples of materials that CHS has created in the past. So a wide variety of silicon nanostructures can be made. So silicon quantum dots with well-controlled size, silicon thin films, so with well-controlled not only particle size but packing into the thin film. So having appropriate voids in the thin film for wetting by electrolyte and things like that, as well as silicon nanowires. So just going back to the silicon nanowire example, so that they can be made with diameters less than 100 nanometers. And so this 100 nanometers, or actually below 150 nanometers is critical to one thing that's been a challenge in the past with silicon-based materials in anodes is that the volumetric expansion leads to rapid loss of cell stability but because CHS leads to materials that have well-defined size and morphology, we can avoid a lot of these issues by making these nanoscale materials. And these silicon nanofibers can be made in a highly scalable process. Yeah. So we see here, and this is, I should preface this by saying this is very early work, so no optimization has been done. And so we see here that silicon nanowires, so bare silicon nanowires have a very high capacity. So this is almost a factor of 8 higher than graphite at a modest charge and discharge rate of 0.2 C. So we see here good cycle life over the first 20 cycles, and then a decrease in the overall capacity. So more work needs to be done here, but the thing I'd like to point out is that the coulombic efficiency of this process remains high. So in addition to making silicon nanowires, we can use the fact that CHS is a liquid to our advantage by directly wetting a wide variety of carbon nanomaterials to make silicon carbon composites. And so those carbon, we can use this liquid deposition to wet the carbon nanomaterials, do the deposition, and create carbon silicon composites easily. And so we see there much better capacity retention over 120 cycles now. So earlier we saw a large capacity fade, and here we have very good cycling, even up to and past 60 cycles. So thinking now down towards the road, so what else can CHS be used for in the lithium-ion battery market? So we have, so I showed those FTIR spectra that showed we can easily tailor the surface of the amorphous silicon. So here we can think of doing that with CHS derived surfaces to improve the SEI, or the solid electrolyte interface, to both improve the lithium-ion conduction and as well as improve the capacity retention. CHS can be readily doped with a wide variety of commercially available materials to give doped silicon anodes for improved stability and better electrical conductivity. And a material that's gaining a lot of interest right now is silicon nitride-based anodes, and CHS offers pathways to make those materials in a very similar way. And those materials have shown to have a very good cycling stability, high capacity, and very good rate capability. So just to sum up, so the value propositions for CHS are an ease and probability, improved yields for silicon-based devices, better control over and a lower processing temperature. So if we're thinking of semiconductor materials, so improved mobility, ease of making dope materials, and so this idea of scalability where it could be directly fed into a commercial roll-to-roll process, as well as when you factor in the cost of the material and the savings that result a more affordable process. Thank you.
All right, thank you, Ramez. Nice overview. If it's okay with you, I want to dig into some of the questions here. And I think we'll start with what kind of carbon supports would work well with cyclohexasilane? Can you give us an overview of that?
Sure. I mean, really, it's carbon support agnostic. So you could use graphene, you could use carbon nanotubes, any one of the high surface area carbons that are typically used, or even graphite.
All right, nice. And can you co-deposit carbon and silicon at the same time? And how would that work?
So you can. So basically, so in a similar process to where you would make a dope material. So here you would just feed some carbon feedstock. There are a wide variety of carbon feedstocks that could be used. So some of the more conventional ones that have been demonstrated are things like acetylene or ethylene, even methane. So they're fed into this reactor, and then out comes a silicon carbon composite.
Okay, nice. And you did touch on this a little bit, but just because it's part of our questions, it's worth hitting again. Do you talk about how the kind of surface that is created by using cyclohexasilane and how that affects the action of the solid electrolyte interface?
Sure. So basically the surface chemistry of the silicon. So you'd like to be able to engineer that in a way where it makes the wetting by the electrolyte more favorable, and it also prevents the formation of a large SEI where it's trapping lithium ions, leading to reduced capacity. So because the surface can be engineered chemically due to these dangling hydrogen bonds that exist, that's where we see that CHS-derived materials have a unique advantage.
Okay, very good. And Ramez, you talked in the beginning about a new synthesis and a manufacturing partnership with Evonik. What is the current plan for when samples will be available?
So we're targeting having samples available at the end of this year. So we'd hoped to have it available sooner than that, but with COVID-19 things got slowed down, but that's the current plan.
Very good. And can you talk about the safety protocols of the material? What is necessary and how does that compare to like the use of silane, for example?
Well, from a safety perspective, I mean, certainly it's a reactive molecule, so precautions that exist for monosilane may exist similarly for CHS. So just the lower vapor pressure of CHS makes it easier to handle, and it doesn't need to be stored and transported in highly pressurized vessels.
Okay. And for people that are interested, where can they get more information and contact either yourself or others at the Coretec group? What's the best way to reach out?
The best way to reach out is the website, and you can see my email address there if you want to reach out to me directly as well.
All right, perfect. Thank you. So I hope everyone enjoyed the webinar. And as Ramez has mentioned, please visit our website. We have a contact us. We would be more than willing to answer any additional questions or have any conversations with you. Any closing thoughts from you, Ramez?
No, other than I welcome your questions and thank you for your attention.
Thank you so much.